Welcome to the tutorial on how to estimate analytical thresholds. In this tutorial you will learn estimation of stochastic thresholds and visualization of dropout data by various plots, multiple and single file import with automatic trimming of controls and ladders, and automatic conversion to the STR-validator format. Start a new session of STR-validator. Put the R terminal to the left and the STR-validator GUI to the right. Click the Workspace tab, and then the Import button. Click the Select Folder button, and open the Input Files folder. Note that the result files have a prefix dilution. Expand the Multiple Files option, and give the prefix dilution. Check the Auto Trim Samples option to trim away positive control, negative controls, and ladders. Check the Auto Slim Repeated Columns option to convert to STR-validator format. Give the imported data the name dilution, and click the Import button. The imported files are output in the terminal window. Click the Import button again, and now click the Select File button. Select the reference dilution files and click OK. Uncheck the Auto Trim Samples option and give it the name dilution ref for the reference profiles. Now click the Dropout tab and the Calculate button. Select the dilution dataset and the dilution reference dataset. We have a total of 84 samples and 7 references. Click the Check Subsetting button. Here you can check that each of the samples are grouped with the correct reference profile. Uncheck the Remove Quality Sensors, because the Fusion kit does not have any quality sensors. And then we can specify the limit of detection threshold to 150 in this example. Leave all the different methods to score dropout checked, and then click Calculate Dropout button. Now click the Plot button and select the dropout dataset. The kit is automatically detected as the Fusion 6C. Click the button to plot heat map by sample. And here we can see that within each serial dilution we have a smooth transition of full profiles to partial profiles with dropout to negative profiles. We can save this plot by clicking the Save as Image button, and I will append heat map sample and select PNG file extension, because this image format is easily imported into, for example, Word. Uncheck the overwrite existing file option and also the load size from plot device option. Instead, we will give the width and height manually as 40 and 20. The resolution can be left at 300 and the scaling factor at 1. Click the Open button and select the output folder, and then click the Save button. Next, click the Average Peak Height button. Here the same data is plotted, but by the average peak height of the sample. And ideally we should have 1/3 of negative profiles, 1/3 of partial profiles with dropout, and 1/3 of complete profiles. Click the Save as Image button to save this plot as heat map by height, and then save, because now all the settings will be remembered from the last time. Next, we can click the dot plot button in the other plots option group. Here we see, here we look at all the dropout, and we can see that they are grouped by dye color. So if there are any differences between dyes, we can easily spot them. Click the Save as Image button again, and append dot plot to the name. Click Save. We can also plot the data as an empirical cumulative distribution plot. Where we see all the observations, and we can get a good estimate of a threshold for dropout. Click the Save as Image button and append empiric ECDP to the name. Click the Save button. It's also possible to plot the homozygote allele peak height within the same plot by checking the option Plot homozygous peaks, and then click again. Now the scale is different because homozygous peaks are high, so we need to go into the axis, expand the group, and change, for example, to 150 to 450 RFU, and then plot one more time. So this have the same scale as the previous plot, and we can click the Save As button to save the plot. I append the ECDP and home for homozygous to this name, and click the Save button. So the data look nice, and we can now close the plot window and the plot. But click the Model button and select the dropout dataset. The kit is detected as the Fusion 6C. Usually when we model dropout data, we exclude the sex markers like amelogenin and any Y chromosome markers. Here we have 4 different methods to model dropout. Let's start with the default one, and we can check the print model option and click the predict dropout probability button. Heterozygote alleles with dropout of the sister allele is located at the probability of dropout 1, and we can see that there are no outliers here. All other observed peak heights are located at probability of dropout of 0 down here, and the logistic regression line goes between those two. We also have the model parameters up in the right corner, and the Hosmer-Lemeshow test statistic. And this, if the value is less than 0.05, the model is rejected because of poor fit between the model and the observed values. It should be noted though that this value cannot be used to rank the different tests. It can only be used to reject a poor fit. We will go back to the plot window and change the x-axis scale to get a nicer plot. Expand the axis group and put in a 0 and then 700 RFU range. Click the plot predicted dropout probability button again. So now the plots looks quite nice. and we have the point estimate where we have a risk of 1% of dropout of the sister allele in a heterozygote pair at a stochastic threshold of 484 RFU. We also have a conservative estimate of 539, where the probability of observing a greater risk of dropout than 1% is less than 5%. We can go back to the model window and check the use average peak height instead of allele locus peak height, and click the plot predict dropout probability again. So now we have changed the explaining variable to the average peak height instead of the observed peak height of the sister allele. So now we only have a few points here, and that is because each sample has only one average peak height. The point estimate of the stochastic threshold is now 440 RFU, and the conservative value is 489 RFU. So we can repeat this with all the methods that we are interested in and collect the important information in a table. And what I would collect is the test statistic, the point estimate and the conservative estimate, and perhaps the model parameters as well. And when you have collected all this in a table, you can take an informed decision on what stochastic thresholds to use. A table of different point estimates and conservative values give you a range of statistically supported stochastic thresholds, and you can select a convenient value within this range. So now we can close the model window and the plot window, go back to the workspace tab and click the Save As button to save the project. Locate the folder where you want to save and click OK. Give it a name, the project, the name STR-validator stochastic threshold, and then click OK and close. So that's it. Thanks for watching.